Ladies and gentlemen, John Belkowitz, Intelligent Concrete. Just wanted to go over this case study. You know, we get to look at some pretty nasty concrete structures that have gone through the trials and tribulations of their localized environment over time. And, you know, normally the question is, you know, rip and replace, rehabilitation. What can we do? What is the least expensive route we could go on to you know, make this thing right? And I've got one here that I like because it's a difficult one. It's something that we see often, and it's a concrete wharf. And if you've never seen a concrete wharf, it's a concrete platform out in the middle of some body of water. You know, the one that I'm looking at right now is a sea, and I can't really release too much information about this. We'll post the picture. But there's concrete posts, piers that are anchored into bedrock within the water, and then sitting on top of that, that acts as the foundation, sitting on top of that, you know, concrete decking. So the concrete posts are usually drilled into the ground, some type of caisson is dropped in and then cast, and then on top of that a column is cast with some type of spread footing on top of that, or cap on top of that, and then a beam goes on top of that, and then we have, you know, a two-way slab design. The thing about concrete wharfs is that they are in an aggressive environment times 2 and sometimes 3. And you know, the question is, how do they fail? Because that's the purpose of these case studies. Review it, and can we come up with a solution? And sometimes that solution is you know, rip, strip, and replace. So the first thing that they go through in how do they fail is this splash/tidal zone, where you have this wetting and drying, this fatigue cycle. And with that wetting and drying comes a volume change. And we've already discussed this in other videos, that concrete doesn't normally like going through a lot of cycles of volume change, and in a tidal and splash zone, that's what you have, and that ultimately leads to cracking. Now, not only will you have cracking, you know, there is going to be some initial permeability, poor connectivity, percolation, if you will. That's just the inherent nature of concrete. So, I mean, we look at concrete and it's a hardened sponge, but when it goes through this wetting and drying cycle, we see more, or an increase in permeability through these fatigue cycles, or cracking from volume stream. And because we have that cracking, we're going to have the migration of moisture and materials that are a little bit more deleterious than the poor water solution that's within the concrete. And you know, normally what we find is, once we get this cracking, once that is induced, then we have the migration of these waters and these salts from the brackish water, and that leads to corrosion of the reinforcing steel. And because we're decking, normally with heavy weights, there's normally a lot of steel, and that means there's a lot of opportunity for not only the steel corrosion, but concrete corrosion, premature failure of the concrete mechanism, or concrete structure. So, you know, that's why we, you know, oftentimes need to come in to make a decision, because not only is it difficult to repair and replace these structures, but when they can't be used, there's money lost. The other way that these structures can fail is by use. Most of these structures are, you know, used with heavy equipment. There's heavy weights. There's ships bumping up into them. So there's some type of load or dynamic movement, wave attenuation of shock loads going through these structures. And, you know, a few structures I went and looked at a couple weeks ago, they are on fault lines. So there's a lot of seismic activity too. And with that, you combine what we just talked about, this cracking from fatigue of shock loads and use, with the normal recurring you know, fatigue cycles from splash zones and tidal zones, and then of course the alkalis and the mag chlorides and the sulfate, whatever is coming from the brackish or seawater, is going to have a negative impact on the steel corrosion and the concrete corrosion. So all that combined, we've got a really harsh environment. So how do we repair these things? while they're in service or as short of a shutdown window as possible. And I see there being two ways. And this assumes that we're dealing with a retrofit. We're not talking about new construction. So if we were doing a retrofit, something like this, there's two scenarios that I see. Non-structural and a structural. Like you first start seeing the signs of the concrete corrosion, the bleeding, some hairline cracks, or you see chlorides migrating, or the concrete is starting to change its shape, becoming more voluminous and maybe flaking off. With that, I would say you can either adopt an electronic protection system, anodic or cathodic protection. I was just looking at an Australian method, a CC135 galvanized anode that act as a sacrifice, that it had the deleterious material attack that item that was placed on the concrete instead of going after the steel. I just started looking at hydrogels, spraying on colloidal silica and other bells and whistles, additives that can be used as a retrofit. What they do is they function as where cracks are formed, the material migrates when it's sprayed over the concrete, and then it uses the alkalis in the pore solution to create bridges between those cracks, in a way healing up those cracks. But it also creates that it goes through a pozzolanic reaction with the colloidal silica. But with some of these products, there's a certain catalyst involved that creates a hydrogel that stops the migration of water, so that even if there is residual deleterious material that requires the migration of water, this stuff would basically reduce the migration. So the last thing is structural damage. And a gentleman by the name of Justin Shook, and I think we already talked about it, posted a video and doing a wharf in Boston Harbor, I believe. And he shows this video where they have this short window, ripped out and replaced a certain bit of concrete. And I don't know if it was a facing, I believe it was structural, because I thought I saw there was some steel rebar cage. But they've got to spray on this shotcrete, and then it's got to set up before the tide comes back in, which is a very difficult process, but obviously can be done, especially to save time and money. So yeah, some interesting methods that are out there. Let us know if you have any questions or comments. Like, subscribe, all that jazz. And we're going to be posting this picture, and if it's not this picture, it's going to be a picture like this. And really take a gander at it and let me know what you think. You can actually see some of the piers going through their failure mechanisms, that volume change of the concrete. And then there is product being applied, but really the failure state is quite amazing. And you also have these platforms that are used to catch falling concrete. So, I mean, just really awesome stuff. So, hope you liked. Have a great day. Go concrete. Beat asphalt.